I've decided to call my talk "Putting the Spark into Spark." This is really all about Apache Spark, but it's a little bit to do with the work that we've done to couple Microsoft's cloud, Microsoft Azure, and Spark. And I know that there are a few other talks around Azure here, so maybe this will be quite topical today, and you can see a different spin on what we've done. Just a little bit about me. I'm the director of a company called Elasticloud. And I've been working with Azure for around about 4 years now, and Spark for just under 2 since the early sort of 0.4 release. I also run the UK Azure community, so I get I see a lot of use cases, and some of the work that we've done with Apache Spark was born out of the conversations that I had there, and I do a lot of contributions back into open source, so if you want to check out my GitHub repo, then you're more than welcome. Still waiting for somebody to contribute. Loads of issues always, but nobody offering their help. So what I'm going to do is I'm going to break this talk down into some sections, and hopefully I'll make this more demo-centric. So I want to give you a background around Windows Azure, even though I'm sure that, or Microsoft Azure now. And even though I'm sure that some other people will during the day, I want to talk a little bit about Apache Spark, and I'd also be interested in speaking to some people afterwards who may be using this at the moment. I'm going to talk a little bit about Spark streaming as well, and why it's very cool. If we get a chance, I'm going to talk about this Spark, how you do machine learning on Spark, and maybe look at an example around recommendations, and we'll look at things like job submission and how this big data framework compares to Hadoop, and what are the shortcomings, and then we'll be looking at a new part of Spark called Spark SQL, and maybe talking about how we put this all together onto Azure. So a little bit about Microsoft's cloud. Just a show of hands, anybody using Microsoft's cloud at the moment? Okay, a few of you, great. So this is basically it, and it really is an ever-expanding picture. We talk about this idea of cadence, and it really sort of comes out with the cloud, because it doesn't matter what cloud you're introducing, but every single week or every single 2 weeks there's another announcement. And for Microsoft in particular, I think this has been a really difficult thing, because coming from that Windows and Office world where you sort of deploy patches and service packs every 6 months, and then all of a sudden you have to completely change these product cycles so that you're just releasing things pretty much on demand, because there's so much stiff competition in the market. So so one of the things that I think differentiated Microsoft's cloud was that they had a good set of platform services. So they built their model initially on PaaS, and Microsoft's sort of interaction with big data has been to sort of customize a deployment of Hadoop. So they've worked with Hortonworks to bring a product called HD Insight to market, and I guess it's not surprising given it's Microsoft's operating system, but they spent an inordinately large amount of money moving Hadoop, which worked absolutely fine on Linux, onto Windows, but HD Insight as a platform service works very, very well, and it supports the normal things that you would expect of Hadoop. It's got Java and Python runtimes, and can pretty much compete with a lot of the other out-of-the-box big data frameworks and clouds like Cloudera and Elastic MapReduce. But they are actually trying to create a big data ecosystem. And their newest addition is a product called Azure ML, which is essentially it's a drag and drop sort of. I wonder how you would term this. Maybe the Lego version of machine learning. So you sort of drag and drop a bunch of algorithms. You do some customizations. You write a little bit of script. If you can write R, you can add that, and then you can couple it to the other tools and technologies that they've got that involve big data. So one of the reasons that we wanted to write our own customized version of Apache Spark was, aside from the fact that we liked it more than anything else, was because we kept seeing this scenario all the time that we were building on Azure. We got very early very early on, we got into the idea of building big data applications for customers, and we always tended to do the same pattern. So some of you might be familiar with this, but this is a derivation of what the creator of Storm, Nathan Mars, calls lambda architecture, which, to sort of cut a long story short, is real-time analytics with batch analytics in parallel. And there hasn't really been a way to do this in Windows Azure, in Microsoft Azure. I'm going to make this mistake throughout the talk. You know, dropping the Windows from everything to do with Microsoft's cloud is really, really difficult after this sort of habit of saying it for 3 years. So essentially, what we're looking at here is a situation where we get telemetry data from an Azure website, and that telemetry data is then republished out onto a message bus. And the message bus will do two things. It will have two subscriptions, so publish subscriber to two different sources, and the subscribers in this case will be an agent that will be picking up these messages and that will be continually persisting these messages to blob storage. So it will just be writing large files, and then at some point during the night, you'll have a scheduler which will just go, let's take all this data and spin up a Hadoop cluster, and then we'll process all this data and we'll end up with less output, which will be more meaningful. And maybe we'll put that into a relational database. And and that trend is really the reporting aspect of this. So every single day, following morning, business wants to report. This is generally a good orchestration pattern. But at the same time, there's now this trend to want these real-time dashboards and, to be able to respond to events and to be able to trigger processes off the back of this. So around about 18 months ago, we rolled our own version of Storm on Azure, and we wrote our own Spout, which we open sourced, and it enabled us to plug into this workflow and pick up these service bus messages and do exactly the same thing and show stuff on a dashboard in real time and be able to build an application in Storm which would sort of respond to these events and be able to deliver emails and alerts and be able to show nice graphs on the web. The point I'm trying to make is that we keep seeing this scenario over and over again, which prompted us to sort of bring Spark to Azure in our way. So just to sort of take a back step and look at what Hadoop does. It's a very, very simple, dumb framework. It's a lot of people in Hadoop would probably, a lot of people that use Hadoop would probably describe this as using a sledgehammer to crack a nut, because essentially that's what it is. It takes in any data source and multiple data sources, and it just reads those. It puts them through a mapper. So that mapper will basically emit a bunch of key value pairs, and those key value pairs will then be shuffled around and will somehow make their way to the right reducer. And so in between, you've got companies that are doing a whole bunch of optimizations and visualizations around this, and and so you've had a really, really good and strong ecosystem. But that comes with a bunch of drawbacks as well, in that you really have to think about your pipeline of data because you've just got these two single operations. So in this case, what do we do if we want to be able to say, let's look at two data sources? Joining in Hadoop is not very easy. You have to have separate rules. All of this is schemaless. So you have to apply this at execution time. So if I want to do anything more complicated, I have to create a whole pipeline where I do data transformations along this pipeline, and you can think of this as separate pieces of software that I've got to deploy every single time. So it's not really that friendly when you consider it. Okay, so let's look at what Hadoop is and how it works. So essentially, we have what's called a name node, or we have multiple name nodes, depending on the level of redundancy that we have. And these control jobs. And these jobs delegate tasks to a bunch of data nodes. And then the data nodes process the data. They sit on top of a filing system called HDFS. And HDFS, the Hadoop filing system, is essentially, as we'll see in some slides later on, is a distributed file system that has resilience built into it. So one of the things that I wanted to show, since this is a talk about Spark and Azure, and I'm just going through these fundamentals in the first 15 minutes or so, is that Microsoft replaced this with the idea of using storage. Very, very interesting paradigm usage of storage, and they built a protocol on top of it called Windows Azure Storage Blob, which also got confused with Windows Azure Service Bus, which I showed earlier. So there were a lot of infighting in teams, again, over names. And nobody still dropped the Windows from this acronym. So it's still WASBA in the protocol. Essentially, HDFS works something like this. So if I want to persist a file, it will effectively take this and it will spread it out over multiple volumes to give me that resilience. And then I just use Hadoop and the HDFS tools to actually write and read to that filing system. So I don't necessarily need to know where it is. But Hadoop does. And we'll have a look as to why that's important. It's important because of this idea of data locality. Wherever the data is, we want to have the compute operation work on this data. Otherwise, what's going to have to happen is we're going to introduce excessive network hops, and we're going to have to pull this data from wherever it is. So Hadoop has to record where this data is, and we have to distribute the workload to the data locality. Otherwise, we're going to be shuffling bunches of data around between all of these various virtual machines and volumes. So if we then look at WASBA, so this replaces this idea of data locality because we don't necessarily need to know where the data is. It's externalizing everything. And the reason that it can do that, so it does work slightly differently from the way that the Amazon S3 driver will work for Elastic MapReduce, and it doesn't bring this down, and it doesn't load it into HDFS. And that's simply because the underlying network that Microsoft has designed in the Azure data centers uses some technology called Quantum 10. And what Quantum 10 does, it's like a mesh between all of the various routes and nodes so that storage is now one hop away from compute. So storage access is very fast. And because of that, you can actually put some numbers on performance and you can guideline around this. So it turns out that actually building this WASBA layer, instead of keeping this on a bunch of virtual hard drives within virtual machines, is actually much faster. Okay, so there is some, so it's the default filing system for HD Insight, and these are stored in underlying blob storage, which is highly scalable. We can have many of these and shard our data all across this. And storage doesn't apply the compute. It's very, very dumb. But what we need to do is we need to make changes to the way that Hadoop adopts this filing system. So there's additions that Microsoft has made to support this protocol as an HDFS proxy so that it doesn't go to this local distributed filing system. Okay, so a bit of background. So we'll now talk about Apache Spark. So Spark is a cluster-based compute engine, and it's highly tuned to do all kinds of different compute operations. It's really good at input-output. It's really good at the sorts of HPC, high-performance operations that require a lot of iterative statistical work. And it can use HDFS. It can use the entire Hadoop stack. And it can also cluster very well. And it's built on these open-source frameworks like Zookeeper, and you can see here Yarn as well. Which makes it very sort of modular. So one of the reasons that that this sort of brings together some of that Lambda architecture that we talked about before, is that it's one of the only frameworks that can do both. We looked at Storm and we looked at Hadoop, and we looked at this idea of batch processing and real-time processing. But what I'm going to show you is that Spark can actually do these two things at once, which actually embodies this Lambda architecture that we're describing. So it clusters, and it can cluster using Apache Mesos. It can also cluster using Yarn, which is yet another resource. I was going to say manager, but Negotiate. Okay, great. And Yarn underpins Hadoop 2.0, and that will basically distribute all of the resources, and using the Yarn API, Spark can sit on top of this, and it can sort of delegate which compute nodes that it's going to be using. If you run it in standalone mode, personally I found this much more efficient, and it uses Akka actors because it's written in Scala to communicate between the nodes. And it sort of looks something like this. So you have a driver program which runs an executable, loads of jar if you like, and it has a special Spark context, and then that Spark context will call out and it will distribute work to any bunch of workers. And you can see that it's sort of decoupled from the resource management with something like Yarn and the Hadoop stack. And you can see here you've got two concepts. You've got an executor which actually runs the tasks. So this is the JVM. But where Spark has its sweet spot is you also have this cache. So you have functions in Spark which allow you to persist data in memory, which is what makes this a lot faster than Hadoop, because you're not stopped by these bottlenecks, these input-output bottlenecks as a result that you get with Hadoop. You can just go to this distributed data set which is running in memory. And it sort of looks something like this. So I can read a text file from disk, I can read a text file using that WASBA protocol that we talked about before, and we can take a simple operation where we can filter all of the error information, for example, from a log. We can then split that error information by doing a map, using the map function. And in each case, what we've done is we've read a file initially, and then we've gone to, we've created what's called a resilient distributed data set. And that RDD is going to have two copies somewhere across that Spark cluster. And it has lineage. It uses a concept called a direct acyclic graph to be able to execute and create these RDDs. And this is something that's just been adopted in Hadoop. So the Apache Spark project adopted this very, very early on. But in each case, you can see that you have a new data set that's existing in memory that you can persist or not persist. You can keep as transient, and you can go back to that as a point in time, any time that you want to actually process that data. So we're going to do a demo of Spark, and I've got a Spark cluster up and running, which I'm going to SSH into, and we're going to take a look at the Spark shell. So this is a cluster of 4 Linux nodes, and they're running on what's called A7s in Azure speak. And I'm using an application called the Spark shell. And what this does is every time I submit an application to Spark, it will create all of the various cluster details. It will create everything that I need, and it will understand where the nodes are, how to distribute the work. I've set this on info just to show you all of the things that are going on in the background, but I've left this cluster with around about 80 gig. And you can see here some of the things that we've been discussing, the use of Akka actors. So it's forming these network endpoints between the nodes because it's going to need to shuffle data between them. Okay, so I get this shell, and I can equally use 3 languages when I interact with Spark. I could use Python, I can use Scala, which is native to Spark, and I could use Java. But there's another shell called PySpark, which we can use just as easily. So what I'm going to do is I'm just going to show you quickly. We've got a data set which we use all the time called Love Clean Streets, and it's data that actually sits in Azure, and it's a whole bunch of crime data around that people report on. So stuff like well, it's actually nothing exotic. I mean, out of the 50,000 events that we've got, most of them are around about dogfowl. But what we're going to do is we're going to run a set of distributed queries now, because it is an open reporting system and the data is on Azure and they have given me permission to use it. And what I've done is I've got a whole bunch of things that I can show you. So I'm just going to run these, and we're going to take a look at the results. So first of all, you can see that I'm reading in this text file. I've already set my Windows Azure storage as the HDFS proxy which we're talking about, and then I'm running a regular expression to split this, and I want to get this by line. I want to get rid of all of the nasty commas and the things that are going to foul up my use of getting the actual data and ending up with more items, array items. But what I'm doing with this code is literally just remapping this, and I'm then persisting this data set and getting rid of the header row. So let me run this. So it will do a count on this data, and it should give me 50,001 rows, including that header. Okay. So I've done that persist. Because it uses a direct acyclic graph, you can see that RDD now is mapped, right? But until I actually do something with it, it's not persisted into memory. So what I'm going to do here is there's a couple of pages that web applications that they've provided, and you can see here that we've got a whole bunch of workers which are connected with 54 gig of RAM, and I've only made 40 gig useful. And we've also got an application. It's a Spark shell, which it knows it's running. We've got an application UI where you can see the commands running, and I've left this on 4040, and you can see that each of these has been running in this way. So you can also see that this sort of 50 meg data set has been stored in memory. It's been stored across two cache partitions. And you can see that it's been replicated. And I can do this ad infinitum until I run out of memory. Although actually Spark can use disk as well. So let's carry on with this, and we'll try and get something more meaningful. So what I want to do with this data, and I'll just show you it briefly, is I want to just show you that that there's a column in here that says cleared, and I just want to get that cleared column. So I'm going to run this, and we're going to data shape this. Now, how many people have used Hadoop before? And quite a number of you. How many people have used Apache Spark before? Fewer of you. So the first thing, if you've used Hadoop before, the first thing that you should notice is that, we haven't needed to singularly write a whole bunch of MapReducers here. What we've done is we've orchestrated, if you like, a data transformation in one piece of software. And this is really where Spark shines, because you can really understand that you can tie the flow of data in with a whole set of commands. Okay, so it's doing a bunch of stuff, and we can take a look at this stuff. We can see the stages that are executing. And if we take a look at things like sorts here, you can see that some of them are running on each of these various machines, BRISC1, BRISC2, BRISC3, which are my workers in this case. Okay, and we'll then take the top 5. So there's a lot of shuffles going on, you can see. And you can see we've ended up with 1,494 incidents, which was the largest number of incidents, and that happened in Lewisham on the 10th of in 2013. And Lewisham does have a lot of people reporting crimes, apparently. But we'll take this one step further. We've taken this up to here, I think. What was the last command we ran? Sort by key. So what I'm going to do here is something that Hadoop finds very, very difficult, which is to join two data sets. So I'm going to take some weather data and I'm going to munge these together here. So I'm just going to run that. Okay, so again, there's a whole bunch of stuff going around and some shuffles. And here you see, we've got, what we're doing is we're passing around key value pairs, and we can define these key value pairs really, really well as array items with strings, int, primitives. And you can see here that, that what we've done is we've taken the districts. This is in no particular order because I haven't ordered this. And we've taken dates, we've taken the area that this was reported, we've taken the number of incidents, but we've also added for that particular month, we've also added the temperature. Okay, and then similarly, if we wanted to push this out, we could end up with a file. We could just completely create our own CSV with the output, and we could coalesce this into a single file using something like that. We just call save as text file. And so in a very short space of time, we've been able to transform this output and resave this so that into Azure storage, so that this could potentially have been, for all I care, as long as I've got the memory or the disk capability, this could have been hundreds of gig, but it wasn't in this case. It was just 50 meg. So I want to move on because I've been rabbiting on and we're running out of time, and just talk through the other part, which is that second area of Lambda architecture. So Spark streaming is the other area of that diagram that we were looking at. We were looking at processing a file. We were looking at how this works in batch. And Spark streaming was designed to read data from a whole bunch of sources. It was designed to ingest this data and then create these into discrete chunks so that we could then take these pieces of input data and we could put this through the Spark engine. But at the same time as that, one of the key ideas was that we can actually mesh this idea of real-time and batch together. So as we've got data coming in, can we look at a history? Can we form trends? Can we do something a bit more innovative? And so, essentially this is what it looks like. We have this high-level abstraction called a DaddyStream, and we can denote the time that that these D streams are actually turned into RDDs, which are the sort of fundamental component of storage for Spark. And we can sort of read these in. And then we can apply operations over this. So over time, we can have sliding windows across these. So those windows are really interesting because even if we collect this data set every 5 seconds, we can say, you know what? I want to take this. I want to keep all those RDDs in memory for half an hour, and then I want to do a sliding window over that. So you can put some really, really powerful things together with that. So one of the things that we did was we coupled the Azure Service Bus, which we've talked about, because we were using this in all of the architectural patterns that we put together for Lambda architecture. And we created a receiver which looks something like this. It's quite easy. If you've got your own sources, you can just tune these to using Spark and then create your own DaddyStream. And then you can write tests. You can see that I've got some things around delivering fakes here. So I've got 5 minutes. So I want to do a service bus demo through streaming. So what I've done is I've distributed a bunch of service bus components here, and I'll just show you what the test harness is, because the test harness is really, really simple. I've written something in Scala, and I've written it to connect to this Spark master here, and I've called this application Azure Streaming Test Application 2, and I've said that I want, after this amount of time, in seconds, I want Spark to clean itself up of these RDDs. And I only want it to use memory in terms of storing the RDDs, and I'm connecting to this custom piece of code that I've written, the service bus stream receiver, and I'm doing a flat map on this. So essentially, I'm doing a word count, and that word count is basically going to go through the complete works of Shakespeare or some other crap that I've downloaded from Gutenberg. And then it's going to print this onto the screen. But you can see it could do a multitude of things. I could have a whole bunch of things going on in the background. I could make this multi-threaded. I could distribute this more so it was doing something more useful. So what I'm going to do is I am going to show you that we could turn, we've used a shell, which is just a Spark application, but now what we're going to do, oops, what have I done there? Oh, sorry, I need to, I'm still running in the shell. So the shell is an application. What I'm doing now is I'm submitting through the job submission interface using a script that the Apache Spark has provided called Spark Submit. And it's doing a whole bunch of work, and that's because it's expecting these recurring messages. So if I just show you quickly, I'm not going to bother logging in again, but you can just about see that there's about 3,000 messages in the queue that I'm looking at. Now, if I look back here, you can see that there's stuff going on in the background, but I've got another tab called streaming in this case. And eventually what will happen is it's assigned these receivers. I've set 3 of them up, and eventually these numbers will be filling up. It might take a couple of minutes or so, but eventually we'll see them.